This lesson is on exponential functions and using now next rules to represent those functions, and then also to look at tables and see if a function is exponential by looking at the data in the table. So the sequence below shows how many bushes Mitchell's nursery planted each year. Which formula can be used to determine the number of trees in the nursery will plant next year, next, if the number of bushes planted this year, now, is known? Well, the first thing to do is to start looking at your numbers. What's happening to the numbers? Well, they're decreasing. And they're not decreasing by the same number each time, but they're actually being halved. So if we look at this, as the now, and this is the next which is this guy, is half of this guy. So our next is half of the now. And then if you look at this, if you switch it and made this the now and this the next is half of the now. So you can just tell that you're multiplying by 1/2 each time to get to the next number. The sequence below shows the number of trees a nursery plants each year, which formula can be used to determine the number of trees the nursery will plant next year, next, if the number of trees planted this year, now, is known. Okay, so again, let's look. So that one's going up by 6, and that one's definitely not going up by 6. So we're not adding the same amount each time. So let's see, are we multiplying? Because A says that they're multiplying by 4, so let's see if that's right. Well, 2 times 4 is 8, and 8 times 4 is 32. 32 times 4 is 128. So next equals 4 times now. Sequence below shows the number of baskets made by South Stokes basketball team. 5, 14, 32, 68. Which formula can be used to determine the number of baskets made the next game if the number of baskets made this game is known? Okay, so again, let's try to find the relationship here. Let's see, I can add 9 to get to 14, but I'm not adding 9 to get to 32. So it's not this one. Okay, this one says it's multiplying by 3. Well, 5 times 3 is 15, not 14, so he's out. Okay, let's check this guy. This says 2 times the now and then plus 4. Okay, so let's check this one. 2 times 5 is 10, and 10 plus 4 is 14. That works. All right, let's try it again. So 2 times 20 times 14 is 28, plus the 4 is 32. That works again. All right, let's try it. Let's move up one, try it again. So 2 times 32 is 64, and then plus the 4 gives you 68. Yep, there's our winner. And then just for kicks, if you want to look at this one, this is now plus 11. Yeah, that works. No, that doesn't work because 5 plus 11 is 16, so that doesn't work at all. So D is out. So when you can't just see the pattern like in number 3, then you can just try each formula and see which one works. Alejandro invested $150 in 2 accounts for 6 years. The ending balances for each year are shown in the table. Which statement best explains why investment B had a larger balance than investment A after 6 years? So these are our times. These are our X's. This is the set of Y's and this is the set of Y's because we have 2 different investments. So what you want to do is you want to look at the differences in your Y's and you want to see how it's increasing. So this is going up $2, up $2, up $2. It's increasing by $2 every time. That's linear because it's increasing at a constant rate. That's linear. Like I said, its slope would be 2. Okay, this one's increasing by $1.95. This one, if you subtract the 2, you get $1.98. So automatically I know it's not linear because it's not increasing by the same amount. That one's increasing by $2. This one's increasing by $2.02. This one's $2.06, and this one's $2.08. So again, I'm just looking and subtracting these two numbers to figure out what it's increasing by. And I can tell that this one is increasing at an increasing rate. And here's what that means. Yeah, these numbers are absolutely going up, but the rate at which they're going up is increasing, because here it's only increasing by $1.95, and when we're done, it's going up by $2.08. So it's increasing at an increasing rate. So this is exponential growth. So let's read. A says the balance for investment B, which is this one, grew at a greater constant rate. And that's not true. It was not constant. The balance for investment B grew at a greater exponential rate than the balance for investment A. Well, B was exponential, but was A exponential? No, A was linear. The balance for investment A grew at a constant rate. That's true. While the balance for investment B grew at an exponential rate. That's true. So the answer is C. So if it increases the same amount every single time, like this one did, then it's going to be linear because it's a constant growth. If it increases at an increasing rate, then it's going to be exponential growth. Sarah did an experiment to compare two methods of cooling an object. The results are in the table below. Okay, so let's look. Here's our time. These are our x's. Here's some y's, and here's some other y's. Our times are going up by 5 each time. All right, let's look at method 1. And we're cooling. So he's losing 5. So every time it loses 5 degrees. That's constant. So that's linear. Okay, and again, I'm just going to subtract these to figure out the difference. That one's decreasing by a -14. That one's a -6. That one's -8. And that one's a -13. This is kind of all over the place. I mean, first it decreases by a lot, and then it decreases by a little, and then a little bit more, and then a lot again. This is definitely not exponential. Exponential has to start out small and get big, or start out big and get small. So let's read. The temperature using method 1 changed exponentially. Well, this is method 1, and we said that was linear, so he's out. The temperature using method 1 changed at a constant rate. That's true. I like that one. The temperature using method 2 changed exponentially. No, that's false, because the change was all over the place. The temperature using method 2 changed at a constant rate? Definitely not. So the answer is B. Number 6, the tables below show values for two functions. What statement about the functions is true? Okay, so we're going to find our difference here. So this is 25 cents, 25 cents, 25 cents, and 25 cents. That's constant, so that's linear. So table 1, or f of x, is linear. Okay, then we look here. That's 25 cents, 25 cents, 25 cents, 25 cents. That's all, not 2.5. That's all 25 cents. So this is linear. So A says the rate of change, which is a slope, is the same for both functions, and that's true. It's increasing 25 cents each time. B says f of x grows exponentially. No, that was constant. F of x equals g of x plus 0.25. No. Both functions grew exponentially. No, they were both linear. Which statement best describes the following table? Okay, so let's see. We've got 5 here, 10 here, and 10 here. So normally we would say, okay, well, that's not constant, and that's not exponential, because exponential would start out small and get bigger and bigger and bigger. This one goes from 5 to 10, which you would think would be exponential, but then it stays at 10. So something's fishy. Okay, so go back and look at your x's. That one's increasing by 1, but look at this one. That's increasing by 2, and that's increasing by 2. So how does that affect our tens? if this increases by 1 and it goes up 5, and this is increasing by 2 and it goes up 10, then doesn't it mean that if there was a 3 in here, that it would be a 5 and a 5? Like it would be, there'd be a 70 in here. And if there was a 5 in here, there would be an 80 in here. So this is actually linear because it's actually increasing by 5 each time. It just goes up by 2 here and only 1 here. So this one is really sneaky, but this one is linear. So it is linear because it increases by a constant rate. Which of the following situations would represent exponential growth or decay? So growth or decay, exponential growth or decay is either going to increase super fast or it's going to decrease super fast. Sam mows the neighbor's yard each week for 20 bucks. So every single week he gets $20. That is linear because every week he makes the same amount of money. Suzanne is raising money for her senior trip. She sells candy bars and makes $30 every week. $30, the same amount every week. That's linear. Bryn has earned $500 mowing yards last summer and puts the money in a savings account which is earning 8% interest. Well, now he's earning interest. He put his $500 in the bank and he's earning 8% interest every year. Well, 8% of $500 is a certain amount of money, and then the next year he earns 8% of his $500 plus his interest before. So now he's earning more interest. So every year he has more money, he's earning more interest off of that money. So that is exponential. Anytime you put money in a bank, that is exponential growth. Tyler earned $500 mowing yards last summer, put the money in a coffee can under his bed. So he's going to have $500 and it's not going to grow at all. Which of the following situations would represent exponential growth or decay? John has $100 in his piggy bank. He puts $10 in it every week. That is linear, constant. Mary's trying to gain weight so she can join the wrestling team. She is currently gaining 3 pounds every week. So the same amount of weight every week. Not happening. Sue is going shopping this weekend and she has a coupon for 10% off her entire purchase at Kohl's. Now that one's interesting because it's a percent and that makes us think it's exponential. But her entire purchase at Kohl's, so she goes shopping and then at the register she gets to take 10% off. Well, exponential growth or decay means it starts small and it gets bigger, or it starts bigger and gets small. This is a one-time thing. So this is not growth or decay. It is a one-time coupon. Jack is on the wrestling team and trying to get into a smaller weight class. He's losing 5% of his weight each week. 5% of his weight each week. So every week he's getting smaller. So 5% of his weight is getting smaller because there's less of him. So this is exponential decay because he's losing weight every week, but he's not losing the same amount. Okay, so just a couple to try. The sequence below shows how many trees Mitchell's nurseries planted each year, which formula could be used to determine the trees in the nursery will plant next year if the number of bushes planted this year is known. So let's see if we can find the relationship here. Going from 81 to 27, 27 to 9, 9 to 3. Looks like we're dividing by 3 each time. Joe did an experiment to compare 2 methods of heating up her coffee. The results are shown in the table below. Which statement best describes her results? Okay, let's look. It's going up 5, that's going up 13, and that's going up 11. That's not linear, that's not exponential. That's all over the place, so that's nothing. Okay, now let's look at this one. That one's going up 25, that one's going up 37 and a half, and that one's going up 56.25. So increases 25, then increases more, and then the next time it increases even more. That's exponential growth. So method 2 is exponential growth. Method 1 is nothing. It's not constant or linear, and it's not exponential. So A, the temperature using method 1 changed exponentially. No, that's false. The temperature using method 2 changed at a constant rate. No. The temperature using method 2 changed exponentially. Yes. There's your answer.